Hello everyone and welcome. Today we're going to explore a fascinating natural phenomenon. The title of our presentation is Earthquakes, with the subtitle, A Force of Nature. We'll be looking into what causes these tremors, how they affect our planet, and what we can do to stay safe. I'm glad you're here, and I look forward to sharing this intriguing topic with you. Let's get started. Let's explore what happens during an earthquake. First, there's the sudden, violent shaking of the ground. This happens very quickly and can be very intense. It's caused by movement beneath the Earth's surface, essentially when energy is released along faults deep underground. You might also notice a deep, rumbling sound accompanying the shaking. This sound travels through the Earth and often alerts us that an earthquake is occurring, even before we see any damage. Speaking of damage, earthquakes can cause significant destruction. They can devastate buildings, damage infrastructure, and alter landscapes dramatically. The impact can be widespread and severe, affecting communities and entire regions. Finally, it's important to understand that earthquakes originate from deep within the Earth. They come from beneath the surface, deep within the crust and the upper mantle. This is where the energy builds up and is suddenly released, causing the shaking we experience. All these points highlight just how powerful and destructive earthquakes can be, reminding us of the importance of understanding and preparing for them within our overall safety strategies. Let's take a closer look at the lithosphere, which is where tectonic plates meet. The topmost layer of rock we walk on every day is called the crust. It's the surface we dig into, build on, and grow our food in. Beneath that, there's the mantle, which extends about 2,800 kilometers deep. The mantle is made up of dense, hot rock called peridotite, which is plutonic in nature. Now, the lithosphere is essentially composed of both the crust and the upper part of the mantle. This is the layer where Earth's tectonic plates are found. These plates are large pieces that constantly shift and move. When they slide against each other, they generate immense tension and pressure, which can lead to earthquakes and other geological activities. So, understanding the lithosphere and how these plates move is fundamental to grasping the dynamic nature of our planet. All right, let's talk about the moment of release during an earthquake. First, pressure builds up. This happens because tectonic plates are constantly moving against each other. Over time, they create immense tension and pressure at their boundaries. Then, at some point, that pressure becomes too much to handle, and it's suddenly released. This is what causes the plates to shift abruptly, leading to an earthquake. When this happens, energy is released in the form of seismic waves that radiate outward, shaking the Earth and causing the ground to move. It's also important to recognize that not all plate movements result in sudden earthquakes. Some plates move very slowly over time, gradually releasing pressure in a process called seismic creep. This slow movement helps relieve stress gradually without the dramatic shaking we associate with earthquakes. All of these processes are interconnected and key to understanding how earthquakes happen, fitting into the bigger picture of Earth's dynamic nature. Let's take a closer look at some essential earthquake vocabulary. First up is the hypocenter, also known as the focus. This is the point beneath the Earth's surface where the earthquake actually originates. It's where the energy is released, causing the seismic waves we feel during an earthquake. Moving directly above that point on the surface is the epicenter. This is typically where the shaking feels most intense because it's right above the hypocenter. Next, we have faults. Think of faults as cracks or fractures in the Earth's crust where tectonic plates meet and grind against each other. Faults can move in different ways, horizontally, vertically, or a combination of both, which is called oblique slip. Finally, there's the fault trace or outcrop. This is what we see on the surface, visible cracks or ridges that appear after a sudden buckle along a fault line. These surface features serve as evidence of the fault's movement and can tell us a lot about the earthquake's history. Understanding these terms helps us grasp how earthquakes originate and propagate, which is key to our overall understanding of seismic activity. Now let's talk about the seismograph and what it does. A seismograph is an instrument used to measure the size and power of an earthquake. It works by analyzing how much the Earth shakes during a seismic event. Essentially, it helps us understand the intensity of the quake. When the seismograph records the seismic waves, it produces something called a seismogram. This is a tracing, a series of squiggly lines that visually represents the energy released during the earthquake. These lines reflect the seismic activity and tell us a lot about the event's strength. Here's a fun fact. Each earthquake creates its own unique seismogram, kind of like a fingerprint. No two earthquakes produce identical tracings, which is pretty amazing because it means we can sometimes identify and distinguish different seismic events based on their seismograms. So, in the context of our overall theme, the seismograph is a vital tool in earthquake study and monitoring. It helps us not only measure earthquakes, but also understand their unique signatures, which is crucial for advancing our knowledge and preparedness. Let's talk about how seismic waves move through the Earth, focusing on P waves and S waves. First, P waves, or primary waves, are the fastest seismic waves we observe. Because of their speed, they are the first to arrive at seismic stations after an earthquake occurs. These waves work by compressing and expanding the rock as they pass through, kind of like how a slinky moves back and forth. Next, we have S waves, or secondary waves, which are slower than P waves. They arrive after the P waves and shake the ground side to side, producing a different kind of movement. Importantly, S waves can't travel through liquids, which is a key point for understanding the Earth's interior. Now, here's the interesting part. The time difference between the arrival of P waves and S waves, often called the time gap, is really useful for scientists. By measuring how much time passes between these waves arriving, scientists can estimate how far away the earthquake's epicenter is. Larger time gaps mean the earthquake is farther away. So, understanding the behavior of P waves and S waves, their speeds, the way they move, and the time differences, is crucial for pinpointing where an earthquake originates and for understanding the Earth's internal structure. Now, let's talk about how we pinpoint the epicenter of an earthquake using what's called the triangulation method. This is a pretty sophisticated technique that scientists rely on. Basically, it involves analyzing seismogram data from at least 3 different seismic stations. Having data from 3 stations is crucial because it allows us to accurately determine the location. Each station calculates how far the earthquake was from it, based on how long it took the seismic waves to arrive. These calculations give us what we call distance circles. Think of them as radius lines drawn around each station on a map. The magic happens when we look at where these circles intersect. The point where all 3 overlap is where the epicenter is located. So, by using data from multiple stations and some geometry, scientists can precisely pinpoint the earthquake's origin point on the Earth's surface. This triangulation process is essential for understanding and responding to earthquakes effectively, connecting directly to the broader theme of seismic monitoring and safety. When you hear about an earthquake being 5.2 on the Richter scale, what that really means is that scientists are using a numerical system to measure how powerful and intense the earthquake was. It's a way to give us a clear idea of the event's strength, and today, we also have more accurate methods for measuring these quakes. The first scale we'll talk about is the Richter scale, which was developed by Charles Richter back in 1935. It relies on seismogram data, specifically looking at the amplitude of the seismic waves recorded during the earthquake. Essentially, the larger the waves on the seismogram, the more powerful the quake. Then, there's the modern scale known as the moment magnitude. This one is considered more precise and takes into account several factors like the rigidity of the rocks involved, how much slip actually occurred along the fault, and how much area the fault rupture covered. It gives a more comprehensive picture of the earthquake's true energy. Finally, it's important to understand the destructive range. Earthquakes that measure between about 5.5 and 8.9 on these scales tend to be the most destructive. They can cause severe damage to buildings, infrastructure, and unfortunately, often lead to casualties. So, these scales help us not only to understand the earthquake's magnitude in a scientific way, but also to gauge the potential impact and severity of these natural events. All right, now it's time to test what we've learned with a few challenge questions. Let's see how well you know these key concepts. First up, what do we call the specific point beneath the Earth's surface where an earthquake actually starts? The answer is the hypocenter, which is also known as the focus. This is a crucial point because it's where the energy release begins. Next, we're looking at the layer of the Earth that includes both the crust and the uppermost part of the mantle. That layer is called the lithosphere. Remember, the lithosphere is what forms the Earth's rigid outer shell and is divided into tectonic plates. Moving on, when tectonic plates intersect and tension builds up, the area along which they slide past each other is called a fault or fault plane. These faults are the sites of many earthquakes, so understanding them helps us grasp how stress is released. And finally, between the two main types of seismic waves, P waves and S waves, which one travels faster? That's the P wave, or primary wave. P waves are the first to arrive during an earthquake, and they move through both solid and liquid layers of the Earth. So these questions highlight some fundamental aspects of how earthquakes originate and propagate, tying directly into our overall understanding of seismic activity. Keep these concepts in mind as we move forward. All right, let's see how well you've understood the material with some challenge questions. First, what instrument do we use to measure the size and power of an earthquake? That's right, it's the seismograph. This device records the seismic waves, helping us determine the earthquake's magnitude. Moving on, do you remember the method used to locate an earthquake's epicenter using data from 3 seismic stations? Exactly, it's triangulation. By analyzing the data from 3 different points, we can pinpoint the exact location of the quake's origin. Now, when a sudden buckle occurs in the Earth's crust, it often leaves a visible crack on the surface. Do you recall what we call that? Yes, it's called an outcrop or fault trace. Lastly, what is the typical magnitude range for the most destructive earthquakes? The answer is between 5.5 and 8.9. Earthquakes within this range can cause significant damage depending on other factors like depth and proximity to populated areas. So, these questions really tie back to understanding how we measure, locate, and assess the impact of earthquakes, which is crucial in our overall study of seismic activity and disaster preparedness. Earthquakes serve as a powerful reminder of the dynamic nature of our planet. They are a natural result of the Earth's constantly shifting tectonic plates, which shape the land we live on. Thanks to scientific advancements, we can better understand these events. Instruments like seismographs help us measure and analyze earthquake waves, while techniques like triangulation allow us to pinpoint where they occur. This knowledge is crucial because understanding earthquakes helps us improve disaster preparedness. Being informed and prepared can truly save lives and protect communities. I want to thank you all for your attention today. Keep learning about our ever-changing Earth, and remember that staying prepared for nature's powerful forces is essential for safety and resilience.